Hi students, myself Dr. K.S.Rangasamy, working as a professor in the Department of Mathematics, K.S.Rangasamy College of Technology. In this lecture video, let us see the topic functions. Now let us see what you mean by function. A function is a relation between two sets A and B such that every element of set A has an image in set B and no element in set A has more than one image in set B. Now for example, let us take set A and set B. In set A, that element ABC is mapped to that element 1 to 3 in set B. So I can say that it is a function. In second example, the set A has the elements ABC, but in set B, the element B is mapped to two images 2 and 3. So it is not a function. Since every element of set A has an image in set B and no element in set A has more than one element in set B. So it is not a function. So it can be written as a function or mapping f from A to B is written as A to B is a rule by which each element A belongs to A is associated with unique element B belongs to B. Next, let us see domain and codomain. The elements of set X are called the domain of F and the elements of set Y are called codomain of the function F. The images of the elements of a set X are called the range of the function, which is always a subset of Y. Now let us see an example. The domain, the first set A, let us consider A, the domain is A, B, C. Codomain is 1, 2, 3, 4, 5. That is the elements which are available in the set B. Next, range. Range is nothing but the image of the elements available in set A. So, domain, codomain and range. Always range is a subset of codomain. Next, let us see an example. Determine whether the following relation is a function with a domain 1, 2, 3, 4. If it is not, give the explanation. Let us see the set R1 given by like this, R2, R3, R4. Now let us see whether it is a relation is a function or not. Now R1 is not a function since the image of 3 is having two pairs as 3 and 1 and 3, 3. The element 3 has two images, so it is not a unique, so it is not a function. In that second set R2, it is not a function since the no image for 3 occurs. Now R3 is a function since every element has an image, but the images are same. R4 is also a function because all the elements are having images. Next, let us come to the types of function. Now we are having one-to-one injective function, on-to surjective function, bijective, composite function, inverse function. These are all the different types of functions. Let us see one by one. Now one-to-one. One-to-one we can say that also injective function. A function f from A to B is said to be one-to-one function if the images of the distinct elements of A under f are distinct. That is, f is one-to-one if f of x1 equal to f of x2. That is, every element of the domain has a single image with a codomain after mapping. For example, let us consider A, that is 10 is mapped to 1, 20 is mapped to 2, 30 is mapped to 3. So this is domain and this is codomain. Each element of domain has an image in codomain. So it is a one-to-one function because distinct element has distinct images. Now let us see another example. In that set B, 10 is mapped to 3, 20 is mapped to 1 and 30 is mapped to 3 once again. So it is not a distinct, so it is not a one-to-one. Now let us see surjective function. Another way we can say onto function. A function f from x to y is said to be an onto function if every element of y is an image of some element of the set x under f. That is, for every y belongs to capital Y, there exists an element x in x such that f of x equal to y. For example, let us take x, y, z, w, which is mapped to a, b, c. I can say the each element of codomain has an image, pre-image in x. A has an image, B has an image, C has an image. So it is an onto function. But let us see this example. The element B, which is available in codomain, does not have an pre-image. So it is not an onto function. Now let us come to bijective function. A function f from a to b is said to be bijective function if it is both 1, 1 and onto. That is, every element of A has a unique image in B and every element of B has a pre-image in set A. In other words, we can say that a function f is bijection if it is both 1, 1 and onto. For example, let us see this set A and B. I can say this as a bijective function because every element of A is mapped to B and every element of B has a pre-image in A. Now here it is not like that, it is not a bijective since 3 is not having pre-image. Then here also it is not a bijective function and here also not a bijective function. Next, coming to the composite function. Now f from a to b and g from b to c be two functions, then the composition of f and g denoted by g composite f is defined as the function g composite f of x equal to g of f of x for all x belongs to a. Generally, f composite g is not equal to g composite f for any two functions f and g. So, we can represent the g composite function like this. F is a function from a to b, g is a function from b to c, f composite g is a function from a to c. Next, let us see one example. The function f and g are defined as f of x equal to x minus 6 and g of x equal to x square. Now let us find f composite g and g composite f and check whether both are equal or not. Now f composite g, let us calculate, that can be written as f of g of x by the definition. That is equal to f of x square since g of x is defined as x square. So I can repeat f of x as x square means x minus x square minus 6. Next, I'll write g composite f. G composite f can be written as g of f of x, that is g of x minus 6 by the definition of f, that is x minus 6 whole square. So it is nothing but x square minus plus 36. From 1 and 2 equation, we can see that f composite g is not equal to g composite f. Now let us see another example. Let f from R to R and g from R to R are functions defined by f of x equal to x square plus 3x plus 1 and g of x equal to 2x minus 3. Let us find f composite g, g composite f composite f and g composite g. Let us find f composite g of x first. That is f of g of x, that is equal to f of 2x minus 3 as per the definition of g of x, that is equal to 2x minus 3 whole square plus 3 into 2x minus 3 plus 1 as per the definition of f of x. When I simplify, I'll get 4x square minus 6x plus 1. Now let us see g composite f of x, that is g of f of x, that is equal to g of x square plus 3x plus 1 as per the definition of f, that is equal to 2 into x square plus 3x plus 1 minus 3, that is equal to answer 2x square plus 6x minus 1 after simplifying the step. Next, we'll calculate f composite f. That is f composite f is nothing but f of x. Using the definition of f of x, when you simplify, the answer becomes x power 4 plus 6x cube plus 14x square plus 15x plus 5. Next, similar way, g composite g, that is g of x as per the definition g of 2x minus 3, that is equal to 2 into 2x minus 3 minus 3 when I simplify 4x minus 9. Like this, we can calculate all the composition of the functions with the basic definition of f of x and g of x. Now let us see inverse function. Inverse function is nothing but a function f turns x into y. If f and g are inverse function, then f of x equal to y if and only if g of y equal to x. The inverse of f exists if and only if f is bijective and is denoted by f inverse. So this is the essential condition for a function inverse, for a function have inverse. For example, f is defined by like this. So f inverse is nothing but just inverse of the given set. For example, find the inverse of the function f of x equal 6x plus 15. Now let us take f of x is y. Then I can write 6x plus 15. From this I can calculate x, that is pre-image. So I can get y equal to 1 by 6 into x minus 15. So f inverse of x equal to 1 by 6 into x minus 15. This is the inverse of the given f of x. Next, let us come to the primitive recursive function. Primitive recurrence relation defines a function where the next term is calculated from the previous terms using simple operations like addition, multiplication, and a specific type of recursion. The primitive functions have been defined as the function on n that can be built up from zero functions, successor function, and projection functions. So these are the main things we can find the primitive functions. One is 0, next is successor, third is projection. Now let us see one example. Show that the function f of x comma y equal to x power y is primitive recursive. The primitive functions have been defined as 0 function as f of x comma 0. So that is x power 0, that is equal to 1 for x not equal to 0. Next, we can calculate successor function that can be written as f of x comma y plus 1, that is equal to x power y plus 1, that is equal to x power y star x, that is equal to x star f of x comma y. Next, define f of x comma 0 as s into g of x, where s g of x is the non-zero test function, and the projection function f of x comma y plus 1 equal to x star f of x comma y. That can be written as in projection form u1 power 3 of x comma y f of x comma y star u3 of 3 x comma y comma f of x y equal to h of x comma y f of x comma y, where h is the composite of the initial functions u and 3 and u3 of 3. Here this represents the position and this represents the variable. Next, let us see permutation function. It is a bijective mapping from a finite set to itself, essentially rearranging its elements without adding or removing. In this, we are having different types: cycle permutation and disjoint cycles, transpositions. The cycle permutation is nothing but a permutation free P from A to A, defined by P of B1 equal to B2, P of B2 equal to B3, etc. and P of x equal to x for all x belongs to A and x does not belong to B1, B2, B3, etc. Br is called cyclic permutation of length R. Disjoint cycles. Two cycles of set A are said to be disjoint if no elements of A appears in both the cycles. Transposition. A cycle of length 2 is called transposition. Next, even permutation. A permutation of a finite set is called even permutation if it can be written as a product of even number of transpositions. Odd permutation. A permutation of a finite set is called odd if it can be written as a product of odd number of transpositions. Now let us see one example. Write the permutation P defined like this as a product of transposition and check whether even or odd. Now from this permutation, 1 is mapped to 3, 3 is mapped to 6, 6 is mapped to 1, and 2 is mapped to 4, 4 is mapped to 5, 5 is mapped to 2. And remaining elements 7 and 8 are mapped to each other. So I can write P as 7, 8, composition 2, 4, 5, composition 1, 3, 6. Because 1 is mapped to 3, 3 is mapped to 6. Once again 6 is mapped to 1. Same manner 2 is mapped to 4, 4 is mapped to 5, 5 is mapped to 2. Same manner 7 to 8, 8 to 7. Now this 1, 3, 6 can be written as a transposition as 1, 6 composition 1, 3. Similarly 2, 4, 5 can be written as 2, 5 composition 2, 4. So P can be written as the composition of all the 3 transpositions, which will give us an odd permutation. Another example, A is a set of elements given 1 to 6 and P is a mapping given like this. Now we have to write P as a product of disjoint cycles and compute P inverse as well as P square. Now P can be written as 1 to 2, 2 to 4, 4 to 1. So I can write 1 to 4. 3 is mapped to same, 5 is mapped to same, 6 is mapped to same. Next P inverse. P inverse can be written as, that is this mapping, then inverse of that permutation. Then finally I have to write 1 to 4, 2 to 1, 1 to 2, 2 to 4. So I can write 1 to 4, then 2 to 1, 3 to 3, 4 to 2, 5 to 5, 6 to 6. Then product of that cycles. Then P square. Like this you have to find the values of the P square, P inverse and disjoint cycles. Thank you for watching this video.